So we'll wait for another 2 minutes. By sharp 6:30, we'll start the session, sir.
Shanti ma'am, can we start? Hello.
Just wait for 2 minutes because strength is 70 only.
Okay, ma'am. Okay.
Kavita ma'am, you can start, ma'am.
Yeah. Okay. Good evening, everyone. I hope I'm audible. I'm Kavita, Assistant Professor from CSE Department. Welcome you all for third day of STTP program. I hope you all are feeling excited and ready for another day of learning and collaboration. As we are gathered here on third day of our short-term training program, I want to take a moment to commend each and every one of you for your commitment to personal and professional development. Over the past 2 days, I have witnessed your dedication, enthusiasm, and genuine thirst for knowledge that has filled this session. It's truly inspiring to see many talented individuals came forward to enhance their skills and to expertise themselves. Now, I want to take a moment and brief about today's resource person, Mr. Kondori Durga Prasad. Sir is a seasoned Tableau certified data scientist and technology lead at Infosys. His driving force in the area of data visualization and analytics with a wealth of experience. He is not only mastered in tools like Tableau and Power BI, but also shared his expertise as a corporate trainer, shaping the skill of over 400 students. Beyond his corporate role, Mr. Durga Prasad extends his impact to academia, member serving as a mentor for machine learning capstone projects at IIT Kharagpur. His commitment to nurturing the next generation of data scientists evident in his hands-on guidance and support. Sir dynamic approach to data science positioned him as a valuable contributor to discussion and initiative exemplifying a commitment to excellence in the ever-evolving landscape of data analytics. Once again, a heartfelt welcome to Mr. K. Durga Prasad, and thank you for being here for generously sharing your time and expertise with us. Let's make the most of this opportunity to learn, grow, and inspire each other. Now, without further any delay, I'll hand over the session to Durga Prasad, sir. Yeah, sir,
Thanks,
thank you.
Doctor.
Yeah.
Thanks, Doctor, for the nice introduction. And good evening and warm welcome to the STTP session for each and everyone. And today, what we are learning is we will be having a session on federated machine learning frameworks and collaborative learning. So, can you please confirm if my voice is audible
Sir,
on the
your
screen?
voice is not audible, sir.
Can you hear me now?
It's very low, sir.
It's very low.
Yes,
Hello.
sir.
Shanti, can you hear me now?
Still very low, sir. What about other participants? Ganesh sir, are you able to hear him properly?
Little noise is coming, madam, at the back.
Sir, clarity is not there, sir.
One second. Is my screen visible?
Yes, sir.
Screen is visible, sir.
Just give me a second. Let me try to.
Some kind of noisy sound is coming. Noisy sound is coming, sir.
Just sorry, guys. Just give me 1 second. Okay. Can you hear me now?
Yes, sir.
Yes, sir.
It's audible, right?
Yeah.
Yes, sir. You're audible, sir.
Okay. Thanks for confirming. Can you also confirm that my screen is visible, my presentation mode?
Yes, sir. Screen is visible, sir.
Hello. Okay. Thank you, guys. Thanks for your patience. And so the agenda of today is we'll look at the definition and few core concepts of federated learning and just
Screen is-
give me a second here. I'm joining
Yeah.
from another tool,
Okay, sir. Okay.
so it'll be able to easy for you. Hi everyone. Hi everyone. Hi everyone. Hi everyone.
Dear participants, sir will join in a minute. Due to some technical issues, like sir will rejoin again. Kindly just be available. Everyone, please be online. Yes, I make you as presenter, sir.
Good evening, everyone. Can you confirm that my screen is visible now?
Yes, sir, your voice is also much clear. And just
Sorry
keep the
for the
presentation. Yeah,
inconvenience.
fine, sir.
Yes, yes. This will be the agenda that we are looking at. We'll be looking at some few core concepts at federated learning, and also we'll be looking at a few algorithms that were like Fed average, Fed proximity, scat fold average, Fed me, and Q Fed average, and we'll compare all those things, all the few major algorithms, and also we'll look into few use cases. That is the agenda for the day. And you also know that, right, as per the previous sessions, by now you'll be able to identify what is meant by federated learning and why we use them based on the privacy issues. And the basic challenge that we are able to identify by using federated learning is non-IIDs. That means non-independently and identically distributed data. So what happened in real-time machine learning? We take all the data, pool together, okay, and make it into the center database. Then we create our model, just like this diagram. See, over here we take everything just in normal, in traditional machine learning. We take all the information from each and every devices and keep it into a central database. And later we create a model out of all this aggregated data where training is focused on centralized training. So there is no any, I mean, here we have the privacy issue and there are also few constraints. But when coming to a non-centralized data, that means if we see on federated learning, we are doing learning without any centralized training data. That means, let's say we are using phone, mobiles, okay, any data or from any devices. There could be any different devices, okay. From these devices, without transferring the data, what we are doing, we creating a model, okay, and we are creating certain output and creating a model, and we are combining all those, okay, and creating our final model. Now, when we say non-IIDs data, that which is a major challenge, right? So let's say that everyone uses your mobile phones and take pictures, right? Let even the pictures that we take will not have any identity or identical. I mean, where the identity would be missing means the heterogeneity of data, which basically some may take pictures of family, some may take pictures of nature, some may take pictures of beaches, right? So the models that we created will be depending on the devices that we use and the nature that we use. I mean, the nature of the person or the model, okay, that we are training will be basically depending on the heterogeneity. So that's why this is one of the major constraints whenever you are using a collaborative learning without any centralized training data. But when we have centralized data, it will be looking on overall data. So if you see the frameworks, right? So there are majorly three federal frameworks that they are mostly looking. One is computer vision applications, okay, which are used in healthcare, smartphone appliances, autonomous driving, and there are high-level APIs and low-level APIs. High-level APIs in the sense image classification, non-ID dataset, data loader, partition methods, object identification, how far the objects are, okay, and Fed Core ML, which are like low-level APIs. Low-level APIs where the security and primitives, okay, and we follow the training engines for this. And if you see on the framework, right, federal learning has emerged as a transportive in machine learning, allowing collaborative decentralized devices while keeping the data in local. Okay, there. Let's see a few prominent frameworks that are evolving in federated learning. One is TensorFlow Federated, which is also known as TFF, developed by Google, which is a comprehensive open source framework, and it extends TensorFlow to enable definition and deployment of federated models. TFF provides abstraction for federation computation along with definition of federated algorithms and the execution of distributed device. And the second one would be which is PySFT, which is supported by PyTorch. PySFT is a federated learning framework built by PyTorch, developed by open-minded. PySoft provides tools for security and multi-party computation, where differential privacy and federated learning is more focused. And in this privacy and security, it is well suited for the application like healthcare, finances, and where other sensitive informations like personal information, personal emails, blood, okay, where such private information could be stored. And there is the third one is FLAR, which is a federated machine learning framework, which is also developed by PyTorch. And the models is provided by high-level APIs and supported by various FL algorithms. Flower allows researchers and developers to experiment with federal machine learning concepts, easy to scale up, and the real-world scenarios. The fourth one would be FATE. FATE is an open source federal AI technology enabler. It supports federated learning scenarios, including horizontal and vertical federated learning. FATE includes learning architecture like high-level APIs and privacy protection for both academic and industrial approach. And the third one is IBM, which is more recent one. And also in the IBM AI, it's an open scale offering allowing organizations to train their models across distributed data sources. And this is one of the model aggregation with differential privacy and a robust solution for the enterprise's distributed data environment. And let's see about few of the algorithms, okay, like federated averaged algorithm in federated learning. Federated learning has received considerable attention in deployment of mobile environment technologies, and based on Fed averaging algorithm, mobile devices need to perform lot of calculations, and it's a time-consuming process. So we proposed edge for like sorry. Yeah. The federated learning is a decentralized machine learning approach where models are trained across multiple devices without exchanging the data. The core idea of Fedaverage is aggregating the local trained model and updating from individual devices and creating a global model. Just like we had an example, right, from each and every personal phones. Okay, all the personal phone data, okay, will be taken by each and every one and created a separated model, and it combines overall algorithm using a global function. So the privacy constraints for each devices are maintained. So in how it will take care. So the global training is on centralized servers, and the individual devices, okay, which we call it as clients, receives a copy of each global model. And local training, client trains model on locally using their own data, The local training process can involve multiple iterations, that means multiple epochs, so that we could improve the performance of the training. The local training, each competent, a local based update. So every local will having one competent, and we could have a number of parameters settled for that, and we could have different parameters for each and every client. And for the aggregation, model updates from all the clients sent to the server, central server. The central server aggregates and obtain a global model. And by looking at the calculations, let's say if you are looking at mathematical representation, it would be a weighted average. Weighted average would be giving more importance to device with larger sets and better training conditions. The weights are assigned based on the amount of data on each device. If you see the mathematical calculation, it would be on weighted average for each and every iteration on the client's network. Okay. So N is the number of samples, CFI is client. So, and over here, what is the challenges that we're having on Fed average is the non-IID data. Just like what we said, right? The non-identical data, which is more specific. And when we are looking at Fed average, this used to be a bit slow whenever we are having a non-IID data. The application fields are mostly into healthcare, finance, and edge computing for the Fed average. But whenever you're computing in image classification, okay, or classifications, Fed average would be a bit slow rather than the algorithms that we'll be looking in the next stage. Okay. Just give me a minute. I will be sharing you the code of the Fed average. Okay. Just give me a second. Okay, that's fine. Let's skip that. The second one would be Fed proximity algorithm. So what we do in the Fed average algorithm, we take all the classifications and from each and everything, and we average them based on the differential weights. But in Fed proximity, what we'll aim is we'll try to converge. Okay, same the federal algorithm settings, but what we include the proximity at the summon level. Okay, what are the differentiation between this one and this one is the objective is federation. In FedProx, it modifies the global function by adding the proximity term. Okay. Initially, the local training and the model update are set up and similar to the Fed average. And the model clients and aggregation are just one thing where you will be having proximity term adding in the duration. If you see the medical one, right? I mean, mathematical expression, this is the same expression that we are having, but the loss function will be having a difference between local and the proximity term while calculating the aggregation. The model parameters to stay close their local models providing regularizer. The proximity term encourages model parameters to stay close for the local models. And one more thing by using the proximity is it mitigates the issue with the non-IID data and improves the generalization that which can't be done in the federated algorithm. The choice of regular parameters is crucially depends, and that's why the cross validation is more important in this technique. That's why hypertuning and optimal values, okay, to be set while we creating the Fed proximity algorithm, just like learning curve and these things. And generalized improvements is like where you include the performance on the global model. The third one is stochastic controlled averaging for federated machine learning. So this is also a central model is trained without every transmitting client data over the network, thereby ensuring basic level of privacy. Okay, this is also a centralized model, but over here it was trained in every client data or the network, ensuring the basic level security, and we investigate stochastic optimistic algorithm for federalistic learning. The key challenges where we're dealing with unreliable and relatively slow network connections. So over here we are dealing from one network, one local network to global server, right? So by transmitting, so there would be a slow network connection between the client server and the main server, and only small subset of the client data will be able to train at a given time. You can't do all at once over here. Okay. And large heterogeneity that which caused with non-IIDness is also presented in different clients. Okay. The most popular algorithm is Federated, but it won't tackle the non-IIDs. So to improve this heterogeneity, Scaffold has created an averaging algorithm which tries to correct the client drift, that which ensures and gives an optimistic for stochastic averaging by reducing the non-IIDs. Okay, so it will try to eliminate, okay, or clearly drifts even if you use a batch gradients for the client participate throughout the training. As a solution, he tries to correct the client drift by estimating the update direction of the server model and the direction of the client. So the difference from client and the global server is estimated as a client drift, which is used for the local update. Okay, the N of F, the initial function that we are looking minus over the client drift is considered as the scaffold averaging algorithm. Alternatively, one can see the heterogeneity as introducing client variance in the updates across different clients and then perform client variance reduction. In the viewpoint of scaffold is unaffected by client sampling. So we'll be having different samplings over here. And while accommodating the heterogeneity is important, and equally the method that we take to avoid the similarities from the client data. The sampling technique that we use to avoid the similarity of the client data is also important. And in scaffold, it is in such a property where variance rounds of communications when the clients are more similar, because once there should be used more epochs while there are more heterogeneity or more similarity in the data. And scaffold is considered as the best algorithm while we creating this one. Across all the values, right? Let's say we take admits data set. Across all the values that we observe, scaffold outperforms Fed average, Fed prox, okay, and also the SGDs, gradient descent, scholar gradient descents. Okay, however, Fed average for heterogeneous clients, and whenever there is 0% familiarity, then only we'll be able to use this scaffold. And whenever you have more heterogeneity, right, the Fed average would be failing, and that's where scaffold average would be the best solution. Scaffold averaging federated learning. And third one is FEDME. FEDME is a federating learning via model exchange. FEDME is a heterogeneous personalized federated learning method with automatic model structure tuning. Okay, so over here, after the clients initiated the model, FEDME starts with learning process. First, the clients send their personalized data to the server. The server clusters the model using unlabeled data. Okay, for the FEDME, it creates a model where it takes all the data from the client network to the server and create clusters using unlabeled data, and each client receives a model. Data belongs to the same cluster as exchanged from the server. Each client trains the personalized and exchange models and determine the index to the new personalized model. So each client sends two models, one to the server. Okay. Both the models to the server. The server aggregates each model by averaging their parameters and send them to each client. The steps are repeated until global communication becomes T. We explain detailed procedure in initializing model training models and model tuning, model clustering, and model aggregation. FedMe first requires the initiation of model architecture to the clients. Since the clients has arbitrary model and architecture in FedMe, they can determine their model's architecture depending on their local data. For example, let's say the client built an optimal data on their local data, and the server can determine the attributive models and distribute them to the clients for model training. In FedMe, each client exchange their personal models. Thus, the model trained in local has multiple data from the clients, which enables the training models even when the client has model with different architecture. Each client trained their personalized and exchange model data by deep mutual learning. Deep mutual learning between personalized and exchanged models improves the accuracy compared to the training and independently trained models. So FedMe is better than Fed average whenever we are using from the local data to wherever we have heterogeneity. Indeed, it is also known that mutual learning effect improves the inference performance of the models when we use numerous models from training. The algorithm of FedMe takes the global round computation where so this is how the framework looks like. So each and every model, okay, let's say from each and every model, from one over here, the model training and tunes, and it will go to the level 2 where the model will be clustered over here and go to the third layer for the performance tuning and later to the main server. And this process continues for n number of epochs until we have an optimized level of T. The later algorithm that which mostly used is Q-fair federated algorithm. The Q-fair algorithm is just adding a fairness. Okay, it is just what we learned in federated learning. The objectives, methods, notions are each and everything are same. But the only thing, okay, the only thing that
excuse me, sir.
yes, sir.
Sir, just we wanted to take a group photo. Can you please switch on the camera? Even I request the participants, please switch on your camera so that we can take one pic. Sorry to interrupt you, sir, in between.
Sorry, just give me a second.
Just 1 minute, sir. All the participants, please, you are requested to switch on your cameras, please. So participants are saying that the cameras are disabled.
Pardon?
Participants are saying that the cameras are disabled. Ganesh, sir.
Madam, I am looking into it, madam. 1 minute, madam. I'm doing the change, madam. Yeah. Yeah, madam. Camera and mic both I have given on.
Now, once you check participants, please.
I have allowed mic as well as camera to all.
Okay, sir. Okay.
So in the meantime, just give me a second.
I request everyone please fast. Shall I ask the sir please start the question? Okay, sir. Durga Prasad sir, please continue. Sorry for the disturbance.
Just give me a second. I have just taken the opportunity to get the codes. Sorry, just 1 second. That is my comments. Okay, that's fine. I'm unable to share the code. Can you please confirm that my screen is visible?
Yes, sir. It's visible, sir.
Yeah. Sorry, guys, I'm unable to share the code. Okay, but if you want, I could explain the code later on. Okay, for a couple of algorithms where I have prepared the code, I will be sending through the mail for you. Okay, ma'am, can you share the code for them? And if I share you,
yes, sir.
what I'll do is I will give an explanation for the code over here. But later, what you could see is you could see the code over the, from my mail. Okay.
Okay, sir.
So let's start with Fed average. Okay. Just. So in this, what we do over here is we introducing the fairness, okay, into the federated learning. So as the weights are higher to the devices, like the performance will be more poorer. Okay. So that's why what we do over here is in like just like a definition, like for the model, it was considered model W provides a more fair solution to the federated learning that model W dash if the performance on model W increases by M devices, which is more uniform, and the performance model will also be increasing. Okay. Let's say in a statistical way. Okay. Natural idea over here is the fairness as defined would be reweighted to the objective as higher as weights to device so that the distribution of accuracies in the network shifts towards more uniformity. So when we reweighing the weights, right? So automatically from the poor performance, it will come to a certain uniformity level. A known optimization is inspired by fairness allocation in the wireless network that encourages more accuracy distribution across devices in the federated learning. The scale method, the tube-fed average, is to resolve the massive networks where the evolution of federated data set demonstrate, which is resulting the fairness and flexibility. Okay, so this is the mathematical equation that we identified. Okay, for any given non-negative cost function and the parameters q greater than 0, right? And this is more recent one. Okay, the Q-fair algorithm is still under development, and there are papers that they are working on. While we say as of now, okay, if we see as per the latest, right, which one would be more comparing all the things like SGD, which is normal gradient descent, scaffold, Fed average, and Fed prox, And even for the comparison, right, we don't have this one, what you say, fair federated algorithm, because it is still under process where the research papers are still working on. So if you see on similarity rounds and the speed up, okay, on the table, this was tested on Eminis dataset. Okay, the measure between the algorithms, numbers,
Sir,
epochs.
please switch to the presentation mode, sir.
Sorry, are you unable to see?
Uh,
Hello,
yes, sir.
you're unable to see my presentation?
No, we can see it, but like presentation mode, you just switch over, sir. Slideshow.
It's in slideshow only, right?
No, sir.
Okay, let me reshare. Can you confirm now?
Yes, sir.
It's an overall comparison network from SGD to scaffold.
Yes, sir. Yes, sir. Yes, sir.
Sorry, guys. Okay. So there are extensive experiments done on Eminis dataset. Okay. And the measures have been interplayed between different algorithms like gradient descent, scaffold, Fed average, and Fed prox. Okay. And the study says whenever we have more, it was observed that scaffold is consistently the best across all the ranges that they have tried. And it outperformed SGD, Fed average, Fed prox. Even the Fed prox is more slower on the local update methods, though in some cases it outperformed by SGD. That is gradient descent, guys. But by using regular tuning and parameters, this thing, right? Hyperparameter tuning and regularization and changing the parameters, what would be best is if you could change that, Fed prox could also give you a better results. Okay, but whenever the similarity is zero, okay, Fed average is of no use. So it is always whenever the similarity is zero or the heterogeneity is higher, it's better to leave Fed average algorithm. Instead of that, it's better to go for scaffold or Fed prox, where SGD is more worse than the Fed average. So Fed average is faster whenever we have more similarities. Okay. So when we choose a right algorithm would be whenever we have similarity, it would be Fed average. Whenever we have heterogeneity data, it would be scaffold. And whenever we have medium heterogeneity and where we use hypertuning and parameters for fine tuning the algorithm, then you could use Fed prox. Okay. And let me show you a few use cases. Okay. So if you see on the use cases, right? What are the normal use cases that we see in real day? So just like our cars, we see every day robo cars and these things, driverless cars, right? The federated learning use this to identify what are the elements that they are available in front of you. Okay. And whatever the data that there for each and every car would be there initially. And in the same way, we could use it for mobile phones, where each and every data is inside the mobiles, but not gone through any, let's say if you are using mobiles, right? The personalized data in the smartphones are common ways for federated learning, like word predictions, phrase recognitions, or voice recognitions. And in case if you see on this one, the example that I'm showing, self-driving cars, where computer vision and machinery learning uses to analysis what are there inside around the surroundings and on real time. Okay, the learning will be real time and it will be continuous adaptation of the environment to learn with the diverse data set. And basing on that, it would be used for the real time driverless cars. And also in the manufacturing sector, how the demand is, how the sales are, okay, how the product recommendation system can be outperformed with the current one. And AR VR, how can we use it? AR VR, augmented reality, and virtual reality to use the object detection, assist with remote operations. Okay. And federated learning can also help in creating optimal models. Okay. Like industrial environment monitoring and performing time series analysis, looking at various environment factors, just like our elections that we are having. What are the industries that could grow in recent times? Okay, let's say we have budget. So what are the investments that where they could be uh, could yield more? Okay, to identifying the business decisions, whether the venture capitalists are able to give, I mean, whether they will be able to give a return or not, or in the healthcare system where we handle sensitive data, right? Where the data access is restricted and due to the privacy issues from healthcare like blood samples or testing, the federated models can be trained throughout a secure data for each and every patients and medical institutions while data remains in its original premises, and it could collaborate within major database sets, whereby creating a model for each and every hospital of a patient and clinically. Okay, it gains insights about each and every patient where they are wider from demographic areas and beyond the local institution. It would be more advanced AI technology. Okay, and let's see. So this is how a healthcare sector could be uh, picturized. If you see on this one, right? So each and every data, the community hospitals, research data centers, cancer treatment centers, everywhere you take the data and create a local model and preserve the privacy and later feed into the federal server and make it a global model. Each model will be created on the client's network. So the privacy would be secure for each and every client, and as it is going on global, it would be the data breach won't be happen even if there are any issue with the client server. I mean, the central server. So if you see that mostly the major uh, takeaways that we are looking in a federated learning, right? It is most on more decentralized approach on machine learning models, which gives advantages of privacy protection, data security, and access the heterogeneity data over the centralized machine learning approaches. And three main strategies of federated learning are centralization federated learning and heterogeneity federated learning and decentralized federated learning. And the popular algorithms that we see is Fed average and scaffold. And if you see that, there is a framework which is known as Fed CV framework, which was built on computer vision. Okay, that which is also most popular in the application side in the recent time on the federated learning. And there are few codes that which I want to explain for you. Okay, but I am unable to share the code. But what I could do is I will explain the code. Okay, how it works. Okay. So if you see on Fed average, right, the code is more simple. Okay. First, what we done is we create a simple linear regression model having random weights. Okay. Initially, we start with a simple linear regression model where we use random weights, and later we create a federated averaging algorithm function that represents main Fed average algorithm and iterates multiple epochs, stimulating the federating learning scenarios. With various scenarios, we iterate the same function. What we do is we'll train this on a client mode. Okay. So each and every model will be trained locally for each epoch, for each client mode. We'll create a function which is known as client model and stimulate the model randomly, and we generate the data. And once we generate the data, what we do is we'll create the local labels for it. What we do? We'll create the local labels, and local gradient will be created based on the different predictions and the different labels on the client model. Later, what we update is each client model from weights from using SGD, which is stochastic gradient descent, based on local gradient descent. And once we get at the local gradient descent, after the local updates, we'll move to global server to the global model, where is updated through weighted averages of all the model. The weights are assigned based on model parameters of each client. Whatever the code that I have set up, right? I have set up for 5 epochs, sorry, 3 epochs for 5 clients. The code setup over here would be for 3 epochs for 5 clients, and you will be able to see once you're able to run the code, right? You'll be able to see how the final weights and the global model has been processed. Okay, this is a sample code just that I have created for this, and they have also created for a couple of algorithms. One is stochastic controlled average algorithm. The same thing what we done in Fed average. The only thing is it also starts with federated machine learning. The only change from here and here is we'll create a stochastic controlling averaging algorithm which represents for each and every averaging and iterates same multiple epochs for the federating learning scenarios. For each scenarios, we'll be having one or few epochs. We could increase the epochs or we could decrease the epochs. We could put in random based on the generated data and the local labels. Okay. So once we have the local SGDs, right? So what we do is the local updates will be going to the same uh, global scenario or the global server where the weights are averaged based on control factor and considering the size and parameters of each and every client. This model also has been trained with 5 clients and 3 epochs. The final prints, what you will be getting is weighted average of the global model after processing the federated learning process. And I also created one more with the Fed proximity. The proximity algorithm has been created. The function which we created is on Fed proximity, where it iterates through multiple epochs, stimulating the federating learning scenarios. The same thing, the rest of the things is the only different thing is the local model is updated by using proximal SCDs instead of the local gradient. So for the instead of local gradient, what we'll do is we'll use proximity in this, and the updated regularization term will be impacted between the difference of local and global weights. Okay, the main difference between this one is the proximity and the proximity update, and the rest of the things are same. And finally, the global weights will be considered based on the introduction of proximity in the same Fed average. So if I am able to see, I am able to show the code for you, but what I'll do is I will send through email over here. Fatima, any questions?
Dear participants, if you have any questions, like you can raise, you can write even in chat box. Dear participant, do you have any questions? Me give the permissions, sir. Sir, 1 minute, sir. I'll give the permissions. I think I have not given permissions.
Sure, sure. And if
Yeah,
you're interested, please let me know. I'll be also sharing you the uh, algorithm
yeah,
thesis, the algorithm papers with you if you require, if you are more interested.
yeah. Sure, sir. Yeah, mic is on, sir. Now, like participants, you can ask questions. I have given permissions.
Good evening, sir. Hello.
Hi, good evening.
Sir, this is Mahinder from Geetanjali College of Engineering and Technology, Hyderabad, sir.
Yes, please.
Hello.
Yeah,
Sir,
yeah, you are
actually, I
audible,
have one.
Mahendra.
Yeah. So I have one doubt, sir. So here, so, can we run these local models on homogeneous and both heterogeneous, sir? Hello.
Yeah, in local, right, you could have any data. It would be homogeneous or heterogeneous. So it's on overall data, right? It would be either similar or non-similar. Let's
But
say if you have Mahinder,
yes, sir.
let's say if you are having a local machine, okay, whatever the local machine that you have, right?
Yes, sir. I'm following.
So whatever those things, right, it will create a model on top of it. Okay, it could be either heterogeneous or the similar data. So it creates a model on the data that you have.
But here the model parameters have been varied when you're working on, I mean, so when you're training your model on the local machines. So, but the same parameters will be sent to the global networks, the
Yes,
global
the
model,
local
right?
parameters and the global parameters would be different while we're looking into it. Local
So in,
parameters could be different and the global parameters would be different.
okay, so means if both are different, nothing will be happen. So means can we get the means correct accuracy or some
Yes,
other?
only for correct accuracy that we do, Mahendra, over here. What we do
Okay,
is, let's say if we have the same thing, okay, let's say your phone has certain, I mean, your local machine has certain things, but this is not the same with all the n number of things that we take, right?
yes, sir.
Or let's say if we're looking at one particular hospital which is on ENT or something, but when we look at the data, we'll have different departments and everything, right? We
Yes,
take
sir.
the patients of different departments and we
Yes,
pull into the central machine or central server. If you give the same parameters, right, that we are training in a different model so that it automatically fails.
yeah.
So they,
Yes.
we need to take different parameters in client model and different in overall server.
Got it, sir. Sir, and one more question, sir. As you said, a flower is one of the tool technique that we can create a simulation of a local mission, right? So, is it possible to create a multiple clients and a server in one local machine, sir, using that flower library or package?
Sorry.
Sir, as you said, the flower is one of the package which we can create a local environment, so federated learning environment. So using that, we can we create a multiple clients and a server environment in one single mission, sir, so that we can test it on the tested federated learning. I mean, approach it. Hello, sir.
Yeah, yeah, sorry. For the federated learning flower, right? So I don't think so it's possible, but let me look into that and get you know, Mahinder. Okay.
Okay, sir.
But normal,
Because
whatever these things, right? So it should be normally for one instance. So we haven't
yes, sir.
tried on multiple instance. So let me check even on this because
Right,
we
sir.
whatever we done is on single instances.
Yes, sir. Actually, as a researchers, if we are interested to do research in a federated learning, we need to show some kind of simulations and we need to
Yes,
show
yes,
results, right? Right.
yes, yes.
Okay.
So what we
Thank you
do
so
is
much,
on
sir.
mostly on a single one. It's an
Yes, sir.
simple deployment tool, right? So
Yes,
in the local mission that we tried only for one, but let's
yes.
see on. Let me see and get back to you on this.
Right, sir. Right, sir. Thank you so much, sir. A very nice presentation. Right, you have given so many insights to us, right?
Thanks, Mahinder.
Sir, there is one question in chat box, sir. Uh, so the question is like, sir, may I know what are the research areas can be chosen from this federated machine learning? Sir, is I am audible, sir?
Sorry, yes, yes. So there are many ways like health research, mobile phones, okay. So it could be on anything, wherever you have privacy issues, right?
Yes, sir.
So everything would be, and where you have security issues or heterogeneity, like edge computing that you have, okay,
Yeah,
and
yeah.
fairness on business idea strategies.
Yes, yes, sir. Like, sir, how about like, let us suppose in future we want to predict at a particular junction how many like vehicles need to get what do you call nowadays? Like we are getting electric vehicles and all. So maybe like later in future, it so happen that instead of petrol bunk we have all the bunks where we can do charging and all. So how do we can predict? Like, can we do research in that stream, sir?
Yes, yes, that you could look on the proximity range.
Yeah,
Basically,
sir.
let's say if you are looking at, this is also a study that which is going on Tata batteries. So
Yes,
where the
sir.
proximity, how much kilometers? Let's say I am traveling from Vijayawada to Hyderabad, or Hyderabad or Mumbai to Delhi. How many
Yeah,
charging stations that I need to be there to ensure
yeah.
that there is no any disturbances from one place to other place? Okay, so
Okay,
they could able to identify each and every, I mean, the proximity of getting a battery charging or getting replaced. Okay, like one would be a
okay.
service station, one would be a charging station. That is a real-time
Yeah,
study which is going on, Ganesh.
yeah, yeah. Thank you, sir.
That's on
There is
battery
one.
recharge and
Yeah,
also on service stations. How far,
yeah,
in how much distance that we need to get in them, so that it would
yeah,
be increasing the battery, what you say,
yeah.
usage.
Okay, sir. Thank you, sir. So there is one question from one of the participants, sir.
Yeah,
Like,
the data processing is similar as ML.
okay, yeah, yeah,
So
sir.
there
That's
is
what.
no special other data processing that is required for federated machine learning.
Okay. Still, anyone is having any queries? Dear participants?
I think no more questions. Kavita ma'am?
Yes, ma'am.
Yeah, please continue.
Um, Thank you, sir. Thank you for your remarkable session. Truly speaking, sir, the way you have explained made the complex algorithm into very simple and coherent way. Basically, your session was not only informative but also incredibly engaging. And also the way of knowledge and expertise were you have, it was very evident throughout the presentation. And the way you are having the ability to communicate complex concept into clear and accessible manner was truly commendable, sir. And the way you have explained the real world examples and practical advice which you have provided to all the participants, it was undoubtedly proven beneficial for all the participants, I guess. So, on behalf of organization community and all the participants, I want to extend our heartfelt thanks for your time and dedication in delivering such a memorable session, sir. Thank you for sharing your expertise and contributing to the success of our event, sir. It was really very memorable session for us. It was really inspiring us, sir. Thank you so much, sir. And
Thank you.
Yeah, over to Dr. Shanti Makka, ma'am, to end note and further brief you about the tomorrow's session.
Thanks, Kavita ma'am. Thank you so much, Durga Prasad sir, for your wonderful presentation.
Thank you,
And
ma'am.
definitely, our participants are gained insights of federated learning frameworks and collaborative learning. Dear participants, tomorrow we have Mr. Brajesh Kumar from ServiceNow. He will deliver a session on federated machine learning for Internet of Things, and he also elaborate how to bridge gap between edge and cloud computing. Thank you all for your patience learning, and I hope you are enjoying this learning journey with us. Feedback link will be closed by 9 p.m. So thank you all. Good night. Thanks, Durga Prasad sir.
Thanks, everyone.
Yeah,
Thanks
thank
for
you all.